part 2 of this session, Big Data Analytics and Internet of Things. For the second part and our second speakers, I would like to introduce you to meet Dr. Shikhar Sher. Dr. Shikhar currently is a Vice President and General Director, Information and Communications Research Laboratories, Cloud Computing Center for Mobile Application from Industrial Technology Research Institute of Taiwan, or ITRI in short. So please welcome Dr. Shikhar Sher. Thank you.
So did everybody hear me okay? Is it okay? All right. So what I'm going to talk about today is really like somewhat my personal view of what IoT technology is going to have. I personally probably attend this kind of talk, probably like hundreds. This kind of talk, like since the word IoT comes about, all kinds of people are given IoT talks, this and that. So I'm trying to inject some of my own personal opinion. So by definition, would be somewhat opinionated. But I thought that would be nice for yes. So I thought that would be nice because that would sort of instigate more discussion and more reaction. Now, as usual, I want to sort of say a little bit. Say a few words about the institution that.
Also, please.
Okay. Okay. So can I use this?
Yeah.
Okay. So I want to say a few words about ITRI. So as you probably know, ITRI is somewhat like NECTEC, but it's not part of the government. It's actually a semi-independent organization, and it has been in existence for about 42 years now. And we have achieved various degrees of success. Like the most famous example would be TSMC, the world's largest semiconductor fabrication process. The institute has about like 5,700 people, and it has a large patent pool, and it does an excellent job in terms of tech transfer. From the very beginning, ITRI is set up in such a way that it doesn't want people to publish papers. It just wants people to transfer technology. That's the KPI. So it makes it a very different sort of organization compared to all other industrial research labs. And then it has a bunch of labs, and the organization that I'm in, I now own two organizations. One is this Information and Communication Research Lab, and the other is Cloud Computing. They are going to be merged by the end of the year. So together, they are about 1,000 engineers in these two organizations combined. And then in the past couple of years, I just so you know that ITRI is engaged in this kind of activity a lot, that we want more visibility. So apparently in sort of like national labs around the world, there's this like an Olympic game kind of competition, which is called R&D 100. So from the very beginning, we cannot get too many awards, and up to more recently, we get them all the time. So this says that it actually gives ITRI a lot of visibility, and a lot of the technology here actually get a lot of inquiries about how it's working and so on. So it's actually a very effective marketing tool. Okay, now back to the theme of the talk. So we hear from the previous talk, like roughly what IoT is. To me, it's really an old idea, right? What it basically boils down to is that you attach some sensor to something, some devices, so you can sense. Once you sense that thing, then you collect them into some backend, and then you analyze it in some way using big data, machine learning, whatever you want. Then you analyze it in some way, and then you react. Then you change the world a little bit to make it better. Okay, so that's basically what it is. You sense, you collect, you analyze, and you react. Now, if you look at it and you are in a computer science field, you say there's no big deal. That's exactly what people do, right? Like, almost every computer system that we are building today fall into that category. The only difference is just that you have so many sensors attached to so many devices that previously you would not think attaching sensors to them. That's all. But things like we are used to ideas like feedback control, data-driven, or a couple of years ago, IBM kept advocating the idea of smart Earth, smart planet, smart whatever, right? Smart everything. But that's essentially what it is. So if the idea is old, then what's the fuss? Why are we sitting here, like listening to people like me talking about IoT? Okay, so that's what we want to find out. So there are a couple of examples that fit into that particular sort of like pattern, like smart grid. So the idea of smart grid is very simple. If you have a way to actually accurately measure in real time the electricity load and usage information, you can use that information to do good things, to make more efficient use of the electricity resource. Like you can tune in the electricity pricing. You can adjust the electricity generation or transmission or distribution mechanism to make the entire electricity resource usage more effective. So that sounds about right? Or you can do intelligent building. Again, there's nothing special about that. If you have a way to measure the occupancy, how many people are in each room of this building, and you know the general weather and the temperature distribution and air quality, then you can adjust all these things. Right? You can adjust the heating, ventilation, air conditioning, and lighting in order to minimize the total energy consumption of the entire building. That's like easy problem, right? Almost like a homework problem. Right? If I give such a problem to a lot of students, they probably think this is not particularly challenging. So it's doable. It's probably there's some math involved, but it's doable. Nothing special about it, right? So I want to pose a question: what's new? So it's almost like a sort of so like what exactly are the new things that we need to worry about in the IoT era? The first thing is really about scale, right? Now, if we are talking about hundreds and thousands, maybe it's a homework problem. But if it's a millions or tens of millions, then it's not exactly. Just to collect data reliably and inject into database in a consistent and robust way, it's not very clear how to do it. So, number of endpoint devices in a given IoT application can easily exceed millions, especially for consumer-grade IoT devices like wearable devices. And so the idea there is that it just works. Like, no question asked. The objective of built-in IoT system is you have to achieve that level of robustness. It just works. No question asked. It cannot not work, right? It has to work, and you cannot ask people to do this and do that. So it has to be very easy to work, to use, and then it just works. And the other thing is, of course, variety. That's another problem of IoT. Is like there are so many domains. It's not very clear. You can create a system and then reuse that system across so many domains. So by definition, you need a lot of customization. And that means it's not like you just develop some magical algorithm or trick and then you can make a lot of money by selling billions of devices in one shot. Most likely, the business model of IoT doesn't look like that. It's like a large number of domains. Each domain sell probably like 10 million, 5 million, that kind of thing. And then you have to customize your logic around that particular application domain and do your thing, right? So variety itself could be an issue. So if you look at the IoT ecosystem, then we know that there are this level of things, right? So IoT, right? So there's things. So things basically mean whatever devices you have to attach some kind of sensors to them. Okay, so then those devices become things or smart things, and then you need some kind of communication mechanism to transport those sensor information that you collect from these smart devices back to some backend, and then you need to apply some kind of analysis techniques. You have to store the data and then apply some kind of analysis techniques to them, and then eventually you expose all this new thing, new knowledge, new insight that you get from the sensor data into the whatever application that you want to deploy. Right. Now, on the right, you also see that sort of like a possible revenue. So the absolute numbers here do not really matter, but I believe the proportion here are pretty reasonable, right? So if the size of business for things is like 31, then the size of business for communication part of IoT is probably 17 and so on. So that's how you should read it. So the absolute value, once again, are not very important, but the relative ratio among them is pretty okay. Right, so that's what we are. And then from there you see that, of course, the biggest chunk is on the application level. Right, so you take all these sensor value, you do some analysis to them, and you try to make some value out of it. It looks a big chunk, but it's not a single category. It actually spreads out over a large number of application domains. And within each domain, you have to do the work. So that's the problem I'm talking about, variety. Right? It's not like if you do something, then you can get all this money. It's not. When you do all the work, you probably can focus on a particular application domain and make some money in that domain. But in the next domain, you probably have to do, certain amount of work in order to reap the benefit of that particular application domain once again. Okay. So now I want to start with the hardware part. Right? In Taiwan, people talk about IoT purely from hardware's point of view. That's because Taiwan is very good at building hardware, especially those guys who are building IC. So they already go through PC era, go through smartphone era, and they think, what's next? What are the kind of things that a single person can have multiple devices of? And then they think of IoT. Like, you have like 6 billion, 10 billion people in the world, and every person has a certain number of devices. Wow, that's a big number. So that's the market I should go after. Now, that thinking is not exactly wrong, but it really is not really capturing what IoT is really about. So my personal view is that IoT device hardware is, of course, indispensable. You need to have IoT device, but it's not where the value is. That's also not my own personal insight. Everybody is saying that. And yet, even though it's not the true value is itself size, it's pretty big. So it's still a pretty healthy market if you want to in that space. There's still a lot of things that you can do. So for example, we can develop various kind of sensors. That would be interesting, right? Things like you can do vital sign, or like what people are talking about, Industry 4.0 for various kind of manufacturing process, like fabric manufacturing process versus metal work versus car component and everything. There are a lot of things that you need to develop new kinds of sensor in order just to sense the kind of things that you want. Like you are in the aerospace industry and you want to inspect when you screw something in an aerospace component, is it tight enough? Is it tight enough that it can last 10 years without being loosened up? Do you have a sensor to tell me, is it tight enough or not? And that sensor alone is very valuable, for example. So like, or things like non-invasive blood sugar measurement. That's the kind of thing that Google recently has. They build this kind of blood sugar measurement into the contact lens, for example. So that's an interesting sensor that we can do. And the other thing is low power and heterogeneous system design. Of course, for a lot of these IoT devices, either it's for environmental monitoring or it's for wearable device, it has to be low power, right? So there are technical challenges that need to be done. Heterogeneous system means that you don't want to build a single IC. You probably want to get a bunch of IC and bare die and package them in certain way. So you can build multiple devices independently and using packaging techniques to put them together. And that's what it means to do heterogeneous system design. And finally, you need sustainable system design. What you have, just devices, but it has to become a module, and you have to be put out of the field. So it has to be self-sustainable. Things like energy harvesting. You can harvest energy from the sun, from a thermal, from even like sort of like a mechanical pressure and so on. You can self-sustain yourself. And you can do self-diagnosis and so on. And then you can do strategic redundancy. Like when you place a large number of IoT devices, you have to put in enough redundancy. So any of them fail, the whole system still works and so on. And the other issue of IoT hardware is it also reflects what I just said, that one of the property of IoT business is variety, right? So it means that when you build this IoT hardware, fundamentally you run into this problem, large variety and small quantity. And then how do you deal with that? So you know that you can build these IoT devices, but every time I only can give you like 100,000 pieces. It's nothing. For most of the company who are doing smartphone, manufacture smartphone or manufacturing PC, 100,000 pieces, then they will turn down this business. This is like no business. We don't want to do it. But that's the nature of IoT business. Like in a lot of these IoT business, you don't have a large volume. You just want to try this and then get into this business, and that's the nature of the business. Then how do you deal with this problem? When you do hardware manufacture, you have to deal with this large variety and small quantity problem in the IoT space. So that's another issue that we need to worry about. So in low power design, I just want to briefly mention that what we have been working on. So the simple thing to do is, of course, you do ultra low voltage circuit, right? So we all learn in IC design, you probably use a 5 volt, 3 volt, 1.2 volt, and so on. Now we can do about 0.25 volt and maybe down to about 2.2 volt and so on, and then we can get the circuit to work. But of course, one of the challenge here is that when you go down to that low operating voltage, then you have to have a way to deal with the fabrication process variation, right? So like different fabrication run, they may have different variation, and so your circuit design have to be able to tolerate this kind of variation. The other idea is that in the first idea is when the circuit is operating, you try to reduce the amount of power it uses by lowering the operating voltage. So that's one idea. Second idea is don't turn it on most of the time, right? So that's like normally it's off. So if you are asked to design an IC circuit and you know normally it's off, like 80% of the time it's off, then how would you do things differently? That's the question. Like usually when we design IC, of course we are designing normally up, right? The circuit is running, right? But now in the IoT space, maybe we should design our system in such a way that it actually optimizes the scenario in which normally it's off. It doesn't run. It's occasionally you wake up and do some stuff and do things. So that's the idea of normally off computing. And the third thing is the idea of event-driven sensor design. So for example, in a lot of this environmental sort of monitoring IoT application is that you deploy all these sensors in the environment. And all these sensors do is that periodically, like say every 10 seconds, they wake up and then they sense a little bit. Are there anything that I need to worry about? And if there's nothing, then I go back to sleep. So every 10 seconds, I wake up, and are there anything that I need to worry about? If they are, then I send them back, right? So this idle loop, this notion of wake up and check loop itself, it becomes the last frontier that we have to deal with. And the idea of event-driven sensor design is we want to push that interrupt idea to the extreme, right? In this environmental sensor, if there's a way to say that if the sensor value isn't big enough, then wake me up. Let's say that's what I want, right? I'm sensing some environment variable, and if that environment variable, the thing that I'm sensing magnitude is big enough, then it can wake me up. Then I don't have to do this periodically wake up and check business. Then the whole thing is really event driven. If the thing that I'm trying to sense is not big enough, it's not worthy of my attention, I will not wake up. If it's big enough, then you will trigger me. So if I have a circuit design technique that can achieve that level of things, then I can achieve the minimum power consumption. Either I need to worry about it, then I'll wake up, or I don't need to worry about it, I don't need to wake up. Either way, I win. So that's the idea of event-driven sensor design, that everything, whatever you are sensing itself becomes a turn-on switch. If it's big enough, it will turn me on. If it's not big enough, then it is not deserving my attention, so I don't need to spend the kind of power to pay attention to it. And that's the idea of event-driven sensor design. So now the next thing is about business opportunity. So the hardware part I already covered, right? The next thing people always ask is that, so who is the business idea? Okay, my idea is that, this is what I'm trying to say, your guess is as good as mine. So, like I say, I attend a large number of talks. In the end, they give you general direction, and that's pretty much it, right? Anything behind that becomes a trade secret, really. If there is a really good idea, they probably keep it to themselves and go out and start a business. They probably would not announce it in a seminar like that, right? So the way we think of it is that the only way you can do things is you try to explore as many ideas as possible, right? So we all know that in the entire IoT space, the most important thing is you have to have a really compelling business or service model. That's really what it boils down to. But what is it? I don't know. And what can we do? Try as many times as possible. That's the only thing you can do, right? And in order to facilitate the process of trying as many possibilities as possible, we try to make it easier for you to try. So that's the idea of you should build a reference platform for IoT devices. And by now, a large number of companies are already doing that, like Qualcomm, Marvell, Intel, Taiwan's MediaTek, even E3 has its own, or Arduino, like it's a sort of Italian open source kind of thing that allows you to build these IoT devices quickly, right? But then the next thing is typically we know when an IoT system consists of these IoT devices as well as IoT backend service. So we also want to build reference platform for IoT backend service. The idea is that you need to quickly develop the front-end IoT device as well as the back-end IoT service. Together, you have an IoT system, right? So we build this what we call IoT PaaS, platform as a service, to facilitate the development of these IoT backend services. And it allows you to do quick development for the baseline backend service. And if you want to do more sophisticated IoT backend service, it allows you to do this customization more easily, right? So that's what this IoT PaaS is trying to do. So what does it really do, this IoT PaaS? Basically, what it does is simple sensor data filtering, ingestion, indexing, and storage, right? Remember, you have sensor value already collected from the devices, and through some network, you pass on to the backend service. So what this backend service is doing is it provides this kind of service, data filtering, ingestion, indexing, and storage. And you also do simple data analysis and presentation. And as far as the big data style analysis is left to the application. So the application have to do this big data style analysis. But basic data analysis and presentation is taken care of by the PaaS. And it also provides anomaly and alert detection and report. And of course, it provides the usual security, availability, scalability, and so on. Most of all, it's testable and it's manageable. So the idea is once you create an IoT backend service, this PaaS will allow you to test it, right? So usually we create a piece of software, you don't know how to test it, you have to move to a different platform in order to test it. This PaaS will allow you to develop this application and test it in place, all right? So that's the idea. And also, it provides various support to make it more manageable. Once it gets online, becomes operational, it provides various kind of login and logout analysis tool to make it more operatable. So this figure basically shows what it looks like. So usually these IoT PaaS come with some kind of device agent. This system happens to call Cerebro. Okay. So this Cerebro is the IoT PaaS I'm talking about. So it provides this Cerebro device agent that can install on some kind of device. In this case, it's a wearable device, right? And then when the data comes in, you fed into the backend. The backend will perform this shallow event data analysis. That's the basic data analysis I'm talking about, the averaging, the trending, some sort of alert anomaly or alert detection. They're simple kind of things. And then you would try to put it into sort of some kind of database, right? And then in the end, you present some kind of API for the upper layer application to do event query and presentation layer. So all these things are done by the PaaS, except the deep event data analysis. That part is done by the application themselves, right? And in the end, it also provides an access app that can run on a smartphone. So all the blue things basically are taken care of by the IoT PaaS. We think that these are the common set of services that a lot of IoT backend services are going to need. And we are going to build them into these IoT PaaS so that we can facilitate the development of these IoT backend services. Okay, so once you have this, then what do you need to do? If you are using Cerebro to develop an IoT backend service, what do you need to do? You basically need to measure the sensor value and output and then send them to the backend service through that device agent software that we provide you, all right? And then you have to define a sensor database schema and their indexes. You have to define the database table schema. And then you can configure the filtering rule on the device, and this is the main part of the work. You have to write a deep event analysis code. Either you're using big data or using machine learning or using whatever your favorite techniques to do it. And then you write an app to access the stored data, and then you test it, right? So that's the job of the guy who's actually developing the IoT backend service using Cerebro. Okay, so next piece is really about back to sort of like more business kind of oriented thing. And this is a pretty old figure that shows the distribution or what people expect the application of IoT in various domains. So we'll talk about things like manufacturing or healthcare or transportation and so on. Now there's some part which is interesting, which is banking and insurance, which I want to talk about today. All right. So I'll get back to manufacturing just in a little bit, but I thought this part is somewhat interesting. At least it looks, I'm a little bit puzzled by this number. How is IoT related to banking and insurance? All right. How is that possible? And then I do a little bit digging. It turns out that it's somewhat interesting, and I want to share with you what it is. All right. So if you think about the insurance business, the name of the game is really precision profiling. So the insurance is about, if I know a group of people's behavior very well, then I can create a premium that I can still make money, but I can protect this group of people, right? So for example, when I was in United States, when I was studying in United States, there was a saying that we could come up with a particular insurance that specifically for foreign graduate students in the United States. Why is that? Because this group of people tend to be well behaved, okay? And then when they graduate, they tend to get good job, so they can pay for it. And also, most importantly, whenever they have a car accident, they usually don't report to police because they don't want to ask for any trouble. So this is a good thing. This is almost like a perfect for insurance. It's almost like they are just paying insurance premium and they never claim. So that's like a good group of people to insure, right? And then, but you need to know that there's indeed such a group of people that you can identify, and then you can create a premium. That's like a reasonable amount, and yet as an insurance company, I can still make money. So the idea of insurance is what I just say, precision profiling. Now, imagine that we want to use IoT technology to be more accurately understand a group of people. For example, car insurance. So previously, car insurance is based on what? Based on gender and age, and maybe whether you are married or not, and then your sort of the neighborhood that you live in. So that's a pretty coarse-grained information to characterize a person. And based on that rough characterization, I calculate your premium and say, okay, now you have to pay this much for a full insurance coverage, right? So obviously, that's very rough. Now, what if you change a little bit? And this is what actually happens today called usage-based insurance. They say that, first of all, are you willing to put in a sensor into the car? And in that car, then I can measure the following things. Like every day, what's the driving distance? And what's the actual road that you travel? Maybe you travel through the downtime versus on the rural roads. And time of driving, maybe you always study at the peak hours or off-peak hours, right? Or degree of congestion, and most importantly, driving behavior. Like, do you push the stop or you have this abrupt turn all the time or not, right? So if I have all this information about you as a driver, then I can calculate more accurately what kind of premium you should pay, all right? And that's IoT. And in this particular case, it's very interesting, right? Who is going to pay for it? It's the insurance company. Like you as a driver, you probably don't want to put this thing on your car necessarily, but insurance companies say, if you put this in, automatically I deduct like $30. Because that means you probably feel very comfortable that you are a good driver, this and that, all right? And then the whole cost is already covered from the insurance company. Is a win-win situation. No longer they have to ask those good drivers to pay more. They can punish those not so good drivers who pay more, and so on. And that's why it becomes an interesting angle, all right? And the other thing is finance, right? So you probably all know that China has this Alibaba sort of e-commerce service. Now Alibaba already entered this finance business, like in particular loan processing, like to lend money out kind of thing. Why can they do it? Because Alibaba claimed that every loan processing cost that Alibaba can do is probably 1/1000th of the traditional loan processing cost. And the reason is very simple. Alibaba, especially for those already on Alibaba's sort of storefront, right? How much traffic they attract, and what's the number of transactions, what's the total volume, what's the sort of incoming and outgoing rate, and so on. They know everything, right? So if some guys already on Alibaba in the e-commerce store side, they want to apply for a loan, it's very easy to make a determination whether this guy is loan worthy or not. right? And because they can leverage that information. So in some sense, this is not exactly IoT, but the point is that all this transaction record in Alibaba storefront can be captured as some kind of sensor and use it to do this finance service, right? The same thing is now Alibaba actually want to extend this thing to create what's called Sesame Credit Assessment, right? So the idea is that not only you can use it to do this loan processing thing, you can extend it to various applications. And this Sesame Credit Assessment actually based on your credit history. So the actual, do you borrow money? Do you, return the money in time and so on? And your e-commerce transaction record, do you buy stuff? And when you buy stuff, are they dispute and so on? And your personal and family bill payment, like your electricity, water, and your gas and whatever. Right. And finally, these two things are somewhat interesting: authenticity and intensity of online social interaction. If you are some guy that show up in Facebook all the time, and you are talking to people, and people seem to respect you, you carry a lot of weight, then you are credit worthy. All right. And depth and breadth of online social connectivity. How many good friends, how many credit-worthy friends you know? If you know that many credit-worthy friends, you probably yourself are credit-worthy. All right. And then once you have this, then they can come up with a Sesame credit assessment. This thing claim they can use for dating application as well. Right? Like when men and women meet each other, show me your Sesame credit assessment, and it's only about certain number, then I'll probably go out with you, for example. And then deposit for hotel reservation, travel visa. They even claim in the future, when you want to go to United States, maybe they want to see your credit assessment. And if it's a higher number, you don't need to apply for a visa, for example. Okay. So that's the claim. So in the end, like I say, that everybody is looking for unique angles into the IoT space. What are the new business ideas? And I want to emphasize once again, in my opinion, nobody has good answers, or nobody has good answers. Now, we can roughly sort of categorize the kind of sort of subspaces a particular IoT project is in. Either they are in consumer or non-consumer, or they are wearable or non-wearable. So if you ask me my personal picks, I will probably bet on things like this. But once again, they are not necessarily the best ideas, right? It's just, as a caveat. Connected vehicle, things like what I'm saying, that gradually we can know more about what's happening inside a car, right? That sounds like a good thing to have. And manufacturing automation, that's the industry 4.0 that the previous talker covered. And the product support and maintenance and long-term elderly care. This is a particular sort of acute problem in Taiwan because our population ages very fast, right? So this, and also probably in Japan as well. So this is also a very important problem for us. And how to use IoT technology to solve this societal problem is also a very interesting technical and the business challenge. So I want to give a bunch of examples. Some of these probably are familiar to you. So the first thing is this Nest apps, right? So Nest apps, the claim of fame is this Nest learning thermostat. It's basically a thermostat that can learn and then tune your sort of energy use inside a home, right? The interesting part is this. The Nest people explicitly say they are not in the IoT space, even though everybody is using Nest as an example of IoT. But the Nest founder specifically says that they are not. They don't think they are in the IoT space, even though they are collecting data and make use of data and adjust the temperature or the air conditioning and so on. It looks like IoT-ish. But they don't think it's such a big deal. This kind of thing, people do it all the time. So yes, it's touted as a success example of IoT, but just for your information, they themselves do not think they are in the IoT space. Okay. The other famous example is Fitbit. Of course, it sort of pioneers this activity tracker, right? It knows yourself, your day, a human being, a person's daily activity, and then use that to do various kind of things. And so that itself, because it starts, it's a first mover advantage, so it becomes a very successful story in the IoT space as well. Now, the other thing I want to talk about is this notion of mass customization. I think like IoT somewhat already touched that, right? It's like that it's a large variety, right? But I think this is also the society's general trend. Like more and more, we already have smartphone now. Everybody wants to have their own smart home. Their own smartphone's outlook has to be different. The home screen has to be different. Everything has to be somewhat customized to that particular individual, right? So like women's shoes, for example, starting, it's no longer you only have like 10 kinds. Probably you have like 1 million kinds, right? That's what people want. High heel a little bit, and maybe at the front the stretch is a little bit smaller, this and that. And even now in Taiwan, for example, for bicycle, this already becomes a situation. Like just like when you buy a clothes, you find a particular size. Now for bicycle, now they already have shop for you to go in. You can customize a bike for yourself based on the length of your leg and then your stamina and so on to define a unique bike specifically for you as an individual user. Now with that, what it comes down is this Industry 4.0. It's all a very good idea to do mass customization, but how can you afford it? Right? We are used to produce like 1 million pieces of the same thing a day. But now, how am I supposed to do like these are like 5 pieces, that like 10 pieces? How can we do that? And that's why people are talking about 4.0, right? So what 1.0, just for your information, is the use of mechanical production equipment, right? The 2.0 is you use that equipment but driven by electrical energy, and also this is the idea of a pipeline, like Ford, the Model T. And the third generation is using IT and electronic to automate the production process. The fourth generation, Industry 4.0, is the notion of collecting information across the entire manufacturing process and do something about it in order to optimize it. So it's not individual manufacturing equipment. It's about the whole process. How do you do it? And in some sense, Industry 4.0 is an application of IoT. That's what it is, all right? So this is the most sort of like a poster child of Industry 4.0. When German people talk about their thing, they almost always use this example, Siemens' smart plant in Amber. And indeed, it produces a very impressive result, if these results are as good as they claim. All right. So what's the goal of the Germans' Industry 4.0? They claim, even I produce 1 piece, I can make money. Okay. So even you have a product line, you only produce 1 piece, I can still make money. So that's the idea. So then they argue that after the first piece, the second piece comes in, everything is automatic. You cannot tune your manufacturing process, all the time. You have to have a way to do this automated tuning of your manufacturing process. And indeed, this particular plant has achieved a very impressive result, like 7 times improvement in productivity in over 20 years. And the same copy of this plant is now in Chengdu in China. Right. So there's another copy of it, and it seems to run pretty well as well. Right. The key building block is what I say, just like IoT, so you need sensor. But exactly what are we measuring? We are measuring the workpiece and the manufacturing equipment. So you have manufacturing equipment that manufactures stuff, and the stuff being manufactured is called workpiece. So then you are measuring these 2 things. And then you feed that, you use this industrial grade sensor network and communication, feed those sensor value back to the back end, and you do real-time sensor data analysis and feedback control and so on. All right. And the notion of big data, like typically people talk about these 2 techniques separately. One is called cyber physical system, the other is called big data. The simple answer is this. When you have a simulation model of your manufacturing process, and you collect those sensor data, you correlate that sensor data with your simulation model, and then you know how to optimize your manufacturing process. That's called cyber physical. You have a model. If you don't have a model, then you rely on statistics. That's where big data is. But you just use statistics and try to find the trend, this and that. All right. So that's the 2 differences. And like I say, this is a typical cyber physical system. Is you have a digital simulation model, that's a cyber, and you use measures manufacturing errors, physical, to fine-tune your manufacturing process, and so on. So finally, I want to mention this just for the fun of it. Like I say, that we all know that IoT is about sensor, right? So what if I throw in the question that if I have a way to sense your consuming record, right? If I know everybody's consuming record, then what can I do with that data, right? So now I can sense them, right? I know exactly what you buy and so on. Then what can I do with that? And how do I optimize certain things, right? And it turns out that in Taiwan, there's such a thing, right? In Taiwan, there's such a thing called electronic invoice. When you go out to 7-Eleven and buy even smallest thing, they'll give you an invoice, okay? And that invoice now becomes electronic, okay? That thing will actually send to some government place, all right? And so this particular service is trying to say that we are going to archive those things. We are going to archive. If you go to these places that use electronic invoice, then we are going to capture them. And we are going to capture them forever. So I'm going to know your lifetime's spending, right? If you are going to these places that support e-invoice. So it's going to be a personal or family archive of electronic invoice stored in Taiwan's Ministry of Finance. It was originally there, but it only stored there for 3 months, and we are going to archive them forever. All right, so that forever archiving part has nothing to do with government. It's with this particular service. And with this, then you can offer a large number of services, right? Like a targeted delivery or coupon or discount, or you can do Groupon style volume discount transaction and so on. Right? So that's another idea, so somewhat related to my spending book, IoT. So this is my last slide. So we all know that what, Internet of Things and Internet of Everything, like, people are talking about it. I just want to give you some sense of sort of sanity check, if you will, that the really good business ideas are still need to be explored. And the only thing that we can think of is the only way to get there is to try more. And then, from time to time, you'll hit it big. And most of the time, it probably turn out to be a failure. But that's okay. That's the nature of this business. And like I said, the value of IoT or IoE is in data and service. And like you probably are familiar that Google and Apple, they will come up with various kind of platform for people to send their data to, right? And of course, to them, data is where the value is. So they want to own everybody's data as much as they can. And the way to do it is they provide a very easy to use platform for you to send your data to. So a lot of these hardware manufacturers, of course, they'll be compatible with Google and Apple. And that basically means these hardware manufacturers' devices, when they get to their user's hand, the data will get sent to this particular place. And that's the way it is. If you don't own your platform, that's what's going to happen. So the current challenge is that the technology roughly are not problem. Unless we are talking about low power circuit design, this and that. But profitable service and business model remain sort of largely elusive. We still don't have a very clear answer to what are the definite win and so on. But to try as many ideas as possible, you need a tool for you to quickly develop your IoT device and IoT service. And that's why we work on this IoT path. And for smaller countries like Taiwan, we don't have a large domestic market. Then you want to do this consumer-grade IoT, usually it's not going to fly very well. So I think some kind of B2B IoT probably is a more promising bet. And B2B means things like smart manufacturing or Industry 4.0. The IoT application in a more enterprise or business side, that looks like a more promising to us. Okay, so that's all I have. Thank you.
Thank you very much for such a wonderful and extremely interesting presentation from Dr. Shih Ke. If you have any questions, please save a little bit because we have one more speaker and then we will round them up at the end around 4:15, and then we have questions for both of our speakers. Thank you. Please wait one moment for switching computer.
NECTEC for inviting us, and also thank you very much for the previous speakers because has allowed me to start a little bit further into what I wanted to say. They have actually mentioned some of the few concepts that I wanted to introduce, so the first few slides actually have been spoken before. And actually it's interesting how the speaks have actually evolved because we have gone to something very general to some to a much more specific oriented opinion on some issues. And now I'm going to present you a very specific work that relates to some aspects of IoT and big data, and actually something that I've been involved for quite some time. So some of the issues that we have now, as our previous speaker and specifically the previous speaker has mentioned, they have been there for quite some time. Before I continue, just a little bit on a recognition, because this work that I'm going to present here is actually a collaboration throughout many years with many of some of my previous PhDs associate, and here you have 4 of them, which are actually the main ones that have contributed to some of the slides that I'm going to present you. A little bit of, yeah. So the first couple of slides, about 5-6 slides, I'm just going to introduce the Internet of Things again and the big data, but you will see there that there is a little bit of overlapping, and later on I just go straight into one particular aspect that I see relevant in terms of further research, and we just come up with some new ideas on how to deal with this problem. This is totally complementary to the previous 2 presentations, so if there is any doubts, please ask me at the very end, but there is no contradiction on what we're saying. Actually, we're completely in agreement. And then I'm going to, if you want, give some instantiations of this new way of classifying time series, and I will show you some real-time monitoring application. And as our previous speakers mentioned, most of them are quite old, but now with the Internet of Things, it becomes on a different dimension, and we have to deal with it in a different way. And if you excuse me, I will introduce Imperial College, which is where I come at the very end. Yes, I'm a member of staff there. So, okay, so a little bit of the background, and as I said, I'm not going to spend too much time on this because we have gone through it. This is just a slide on the evolution of the Internet of Things. We actually evolved from the very early stages from the web, World Wide Web, second phase, the Internet as of Service, then the third phase, the Internet of People, which is social networking, and now we are in the Internet of Things, which is in a way associated, as you've seen a couple of seconds later, to the fact that we are doing machine-to-machine communication. So Internet of Things is just another driver to big data adoption. And what is the Internet of Things? We have already seen that in several times. Effectively, what we want, or what we will be able, or what we're capable already, this is something that is happening, is the fact that we can interconnect and we can talk amongst different things, different potentially appliance, machinery, train tracks, shipping container, electrical vehicles, power stations, and so on. So the number of entities that we will be able to interconnect are endless. And that means that by default, the fact that we are increasing in interconnecting device the increase in interconnected devices that will bring the Internet of Service also will lead, or is leading already, to an exponential increase in data. And hence, the Internet of Things and the big data are closely related, or one is feeding the other one. So big data, as a first speaker said, it comes in 3 V's. Well, I've added a new one here, but it's not actually the main one that I want to discuss. So we know that it comes in big volumes, variety. We have discussed this 2 or 3 times. The other V that also we need to take into account now with this many issues that are happening, the fact that we will have some sort of uncertainty related to the data that we are actually receiving. And the one that I want to concentrate, as both previous speakers have highlighted, is the fact that we will need to cope with often real-time speed of arrival of raw data. So again, just a little bit again to to highlight you where is that I'm trying to concentrate. I'm here showing you the data life cycle. Actually, these are traditional data life cycles, right? It took from two particular papers. And what we see here is, again, the typical phases of the data. You have an acquisition, you have to manage the data, you have to place it in a certain way, you have to store it, and eventually you have to use it, analyze it, which is the analytics, and eventually the data may die, yeah, or will it be the end of the usage of the data. Now, even though, even currently, we are still dominated in terms of analytics by the customer-centric requirements, yeah, organizations are starting to realize that of the importance of solving operational challenges using big data. When I refer to operational challenge, which will come in the next slide, I'm referring to real-time processing of data, as opposed to offline analytics. Yeah? In other words, extracting information from a database and then applying quite sophisticated analytics tool. So organizations will or are becoming more and more aware that they need to enable speed to action. In other words, to minimize the lag time between the raw data that is acquired and the insight-driven that you will obtain from that data to make actions. Yeah? And actually, that is integrally related to the main application that I'm going to mention to you, which is anomaly detection. But also, at least conceptually here, I just round out two parts of this process of the data, which actually are referring in a snapshot to what is called data representation. Yeah? So there is a key phase there when we are processing data, which comes before analytics, which is how that data, which arrive in raw form, yeah, I will need to represent it. And the last slide, to put myself in the context of what I want to show you, or what I'm interested in the main part of the structure of the framework that I want to present. Here you have the evolution of the end-to-end and the internet. And mainly, I am interested, if you want, in solutions that will take real-time processing and the data stream and processing in real time. So the established big data knowledge and capability are actually essential or prerequisite to enable the processing of Internet of Things data. However, without proper adaptation or some sort of evolution in the way in which we deal with this data, for example, representation of the data on an online processing analytic, we will probably not get that much further on. Yeah? So let's go to data now. What we see in terms of the information that we're receiving from the perspective of data management is just to reemphasize the subject that I want to introduce you, is that we know, as we have seen from the previous speakers, we know how to deal with volume, we know how to deal with variety. What we need to probably now focus on is on velocity. Yeah? It's the fact that we need to process in real time. And for that, in terms of concept, big data technology roughly can be distinguished between the operational side and the analytics side. Yeah, the analytics is once you get the raw data, once you have done some sort of pre-processing, you store it in a database, you make some quite sophisticated analysis, you make some recommendations and so on. The operation is the real-time, if you want, aspect of the collection of this data. And what industry is already realizing is actually you have to combine operation and analytical technologies to go forward. And in that sense, the red arrow there is trying to show what are my interests or what is my opinion in a way. For example, we need generic and global fast solutions rather than application-specific solution. But here I want to make it clear, this is not a contradiction with what we have discussed before, because you will see when I show you where my solution is well below, if you want to put it in terms of hierarchy of what my previous speaker has said. It's actually customized, so it's quite high in the hierarchy. I'm talking here about data, which is very low in terms of the hierarchy. Yeah. So my My problem now is in the transition between data and the next step. The previous speaker problem was what happened all the way up. Yeah, so technically we're very far away. And in a way, what I'm trying to do as a benefit is actually benefit the fact that we can even speed up the customization of solutions. In terms of data streaming now, in terms of characteristics, a little bit of characteristic, a little bit of the way in which we need to deal with it. As I said to you, we need to combine operational and analytics. So we need to support a variety of data, and that's important to the solution that I'm going to mention to you. We need to focus on flexibility rather than conformity, trying to try and solve that problem in a very specific way. And in that sense also, what I'm trying to look at, or the ideas behind what I'm going to show you, is that we need to have a domain-independent framework. Domain meaning it doesn't matter which type of data I'm going to process. Hopefully, and this is like the ultimate solution, I can process this in the same way to present it to the next level, such that the next level can actually can customize. So that's a way. And also, by means of doing these domain-independent frameworks, we are building up the foundations to unsupervised classification algorithms, which are very relevant again. I mean, if we want to be fast, if we want to come up with fast solutions, we will like to have algorithms, in this case, for example, classification algorithms, which are part of the anomaly detection, which would be unsupervised. In other words, I don't need to train them. I don't need to show them a pattern for them to realize this is anomalous or this is normal. And continuing a little bit with data streaming characteristics, obviously data stream is something that is actually quite fast in terms of data consumption. It needs to provide prompt access to relevant information. And what is interesting is that also implicit into this, and implicit into the idea that I'm going to present you, it needs to make pervasive the use of, in general, not necessarily predictive, but any time of analytics as a priority. And I'm going to borrow, actually, because I would have liked, I could have put it, but I didn't. I'm going to borrow something that I heard this morning, also to look into the vision that we need to develop solutions which are referred to as invisible analytics. And that's very interesting. In other words, there will be analytic in different places which are seamless to us. Yeah? I will be able to analyze things at a very low level. Yeah? It was mentioned before a little bit the fact that I will be able to do some pre-processing. It was mentioned that probably it needs to be very simple. What I'm suggesting in my future slides, that it can be a little bit more complex, and I still can do it in real time. So the idea is to come up with real-time online time series classification problem. That will be a specific problem within the context of Internet of Things. And a little bit of connection to actually a report that was made public in December 2014, which is an excellent analysis of the role of the government can play in coordinating and promoting healthy Internet of Things from the UK government. Yeah, that was a commission. This is quite interesting. It came up with 10 very important recommendations, and also as a side product, it actually builds into these 5 cases. The 5 cases, obviously, are not thorough. Is probably the fact that the experts that were there could actually speak a little bit more about these 5 cases. So it's not the fact that these are the 5 cases in which the government will actually, or the UK government will focus in, but you can see there that are quite common, and actually we have seen them in the previous slides. And I'm going to use them mainly to try and classify the different type of anomaly detections that I'm going to use. So it's not that I'm totally endorsing them, it's just that I'm going to use it to make it a little bit more structured, what I'm going to show you. So I'm going to try and show you 3 or 4, at least 4 examples from those 5 cases. And last but not least, this is a slide that I borrowed from a colleague that I'm working now in one project in the European Union, which identify the relevant research areas of Internet of Things and they classify them. And just to mention to you that the area that I'm intrinsically interested, even before the Internet of Things, is in distributed intelligence up there, and especially, and you can see that at the very first top, if you cannot read it, it mentioned data representation. So this is something that I'm quite interested for a while now. So let's focus now, and I'll try to pinpoint and try to continue the line of my exposition by just trying to concentrate on one important online big data application. Before that was not big data, but now we have the fact we have a lot of information, and what do we do with it? Which is real-time monitoring and anomaly detection. Now, the cases of health conditioning monitoring, as you, for example, monitor and as you sense different, for example, devices, different motor in an industry, as well as anomalies, are classification problems. Yeah. Again, just a little bit of a caveat here, because there are many, if you want, parts of science, of computing science, which are actually overlapping in terms of terminology. So I'm just going to concentrate on pattern recognition, but obviously they are quite relevant. It's data mining, yeah, classification, clusterings, and other, anomaly detection is one of them, but it's one instantiation, for example, of data mining. But just to continue in one line, I'm just going to continue my exposition from now on, just considering a pattern recognition problem. So these are, they are time series classification in the case. Yeah, they're time series classification problem, which involve the time element. And that is very important, but because what we have here in the case, for example, of a monitoring problem, is that we have a time series, but the time series need to consider the time element, because when you are monitoring, the actual successive data that you're receiving are actually correlated. Yeah, and it becomes even more interesting, or whichever way you want to put it, that if we have more than one sensor, there may be also some sort of spatial correlation. Yeah, which actually in a way is good, because it make the actual sensor network more reliable to the fact that some of those sensors may break down, because I know that there is some correlation, I know what is the relationship between that sensors and adjacent sensors, and I can cope. Yeah, it will be a graceful degradation of actually my system, yeah, rather than a complete failure. So pattern recognition frameworks belong to the field of classification methods. Classification method is actually also, or anomaly detection, if you want, is part of a classification method or a pattern recognition. Now, in terms of the pattern recognition problem, what do we have is most of the pattern recognition problems, and also data mining, are actually intrinsically based on two phases. The first phase is actually when you receive the data, you have to represent it. Yeah? So you extract appropriate properties of that element, and actually once you have done that, you present that information to the classification algorithm, which in our case will be the analytics. And that analytics will map the features to a particular class, will identify if this is an anomaly or no. But as I mentioned to you before, there has been quite an extensive amount of work in the data analytic. And as our previous colleagues have also mentioned, there is the technologies there. We have quite a lot of tools to choose, but we have to make a differentiation. The differentiation is that we have static data and dynamic data. And most of the sophisticated algorithms that we have there on analytics are based on some sort of static data. In other words, we analyze it from the database rather than on real time. And this is very important, yeah? Because here, if we start making this differentiation, there is a major concern that we haven't found the appropriate pattern representation or descriptions of real-time series. And well, I think the last line is what I've just said. You see, most of the approaches treat time series as static data. If they want to apply it, and I'm not going to go into many examples here, but for example, a static analytic can be applied to a dynamic day by manipulating or by changing changes on the time series such that the static, for example, sophisticated analytics can actually apply. But this is a way around. What I'm trying here is trying to come up with a way of representing dynamic data such that I can apply any of the dynamics, of the analytics, that are there available, but I've already considered with the representation the fact that there are time correlations, and the time there is a time series. So in terms, I shouldn't do it, but in terms of what I'm trying to do is to work rather in the first phase, which is representation of data, rather than the classification. For the classification, I'm going to use some classical techniques just to show that the representation that we have introduced works. So in terms of pattern recognition, again, on the basic, we can distinguish, if you want, two main areas. Two main areas in which this pattern recognition problem, these analytics have worked into. What the key of this slide is trying to say is that both areas actually are applications specific. So you have structural representation, just to make your sense, structure effectively saying, look, if I know the pattern, if I know the structure of a sentence in this language or that, I can actually match them or try to match them and try to classify what that sentence may be or that word may be or no. Statistical, on the other side, is trying to make some theoretical decisions and try to identify the statistics of the problem and try to describe it in a numerical way. Well, this is actually what I've said, so I'm going to skip this one. And the new approach that I'm going to show you is actually trying to come to terms with the best of both worlds. I'm not going to go too much in details. Obviously, they have been. I mean, this is not. This is like relatively straightforward. And say, look, if you have two alternatives there, one is good on this, the other one is good on that. If we try and merge them, we will get something better. But what people has not been. Still, those approaches in which they combine the statistical and structural have been very domain specific. In other words, you have to study the domain, you have to understand the series, and then you come out with a particular way of classifying them. In this case, I'm building up the structure, but what I'm saying, once you have built the structure, once you have reconstituted this representation of this data, you are not concerned about the domain from where it comes. The idea is straightforward, or relatively simple. It's actually try to change the analysis from the time series, from the time context, into a probabilistic domain. And what we try to extract, this is a very high level representation, show of what the representation is trying to do. We're trying to extract probability distribution function of the series. And then once we are in the probability domain, we will be able to classify, is that particular event or is that particular set of sequence that I see, do they belong to this or that distribution? And depending on what is the probability of belonging or no, you will be able to say, yes, there is the possibility, there is a high probability that I have an anomaly here. Now, I haven't explained what is an anomaly, but it has been, it always comes back when we publish. An anomaly is actually not an incident, so that's very important. An incident is something that already happened. When there is a crash in the highway or even in the street, that is already an incident, that already happened. An anomaly is a precursor to an incident, if you want to put it in that context. It's something that nobody probably has seen before. It's something that it may end up in an incident, or it may not. But the fact is that we need to react to it, and in the probabilistic domain, we're also taking into account that it may be, or there is a probability that even though that particular bit in the time series is slightly anomalous, that slightly anomalous will come back to normal. And that's why the probability domain also helps us in that analysis. This is called, there is another area of research which is called stochastic monitoring, which is a monitoring which is not based on thresholds. The classical control theory says, look, you have a threshold, if you go above the threshold, you have to do something. Stochastic monitor, especially in the case of stochastic series, it tells you that if you're going above a certain threshold, there is a probability that that series will come back again. And that's what you're taking also implicitly in this consideration. What I didn't say something else here is how do we consider the time correlation. I'll explain you one or two more slides. Oops. Yeah. So what are we doing? And here I can actually explain. What actually we're doing is taking the time series there. We apply a multi-resolution decomposition method here. So we're getting a much more rich representation of the signal. In this case, probably can be wavelet decomposition. Yeah, so we transform it to a wavelet domain. Once we have transformed it to a wavelet domain, we have a sparse representation of the original signal, which can be reconstituted on this way back if you want. And actually, we obtain the PDF of each one of the components. So the idea is there. Yeah? The fact that I'm using wavelets, I'm considering the correlation in time. Yeah? So effectively, I am building on the scheme the characteristic of the time series. Now, this is a very simple instantiation of it. What you have there, you have discrete wavelet transform, and on top of that, in order to make the estimation of the density, due to the fact that the student was an expert in wavelet, he used wavelet best density estimation, but you can actually use, this is like a Lego, you can use any wavelet destination, any any density estimation with any numerical technique. Yeah? Not only at this stage, because this is actually the structural generative descriptor I want to introduce you here, but this, remember, is feeding into any classification or any other data mining algorithm in general. So also we can play not only with the blocks here as a Lego, but also we can play with the next stage, which is a classification stage. So in summary, what we have been able to control, or this is what we're claiming, we actually have tested extensively with almost all the data that was available in the web from these institutions around the world. We have been able to sort of claim that we have constructed a very robust time series classification, which, as far as we know, is domain independent. We tested throughout different series, and I'll show you some of the examples in a couple of seconds, which make the framework quite suitable for a wide variety of applications. It can be instantiated online or offline, so that's not a problem. And there is an implicit assumption there that actually is based on treating the signals as stochastic processes. But actually, it's very robust and actually can work with series that are not necessarily total stochastics. Now, in terms of knowledge, and this is what in terms of the information and knowledge pyramid, where is that we're working? So the structural generative descriptor that I just mentioned, you see, is just about applying it to data and actually giving this to the next layer of this information. So we're still very far away, as I said, to the personalized and the way in which we need to customize, which will be at the very top there. Yeah. And in terms of where we are in research, I can just, this is again just to show you, you see we have this matrix here. We have feature extraction. I wouldn't call them simply what we have now, but you can say current, you can say advanced. And then at the top there, you have data mining, pattern recognitions, any other type of algorithms you are. You have simple and advanced. The only thing that we have shown so far is that with very simple algorithm, we have some edge. Obviously, further developments will actually probably will make this structure much more strong, yeah, much more in terms of what and how do we need to classify. The other thing is that, as I mentioned to you, the structural generative descriptor, even though they look quite involved in terms of computational time, as you will see in a couple of slides, we have online implementation or instantiation of them, which actually can solve, for example, can obtain the probability density function online. So it would not be an issue, the speed. Now, if you want to instantiate what I've just mentioned in terms of some sort of application, what we have here, this is a typical, if you want, sequence of an anomaly detection. So you have the sensed or the sensors, you have the real-time data stream. The top there, what we have is the multi-resolution decomposition before obtaining the structural generative description. And because the structural generative description, remember, it maps into the probabilistic domain, what we have there is any type of statistical discriminatory classification or clustering. And that will allow us to actually detect anomalies. Or that's the idea, or classify. Now, the next slide, which is actually something, again, that have been interesting for some time. You see here you have a very simple sensor, is the question of analytics. How centralized or distributed, or where do I want to put my analytics? Yeah, hopefully seamless, invisible. So the question is, do I just want to send the time series and be processed somewhere else? It may be local, it may be central, or do we want to do some pre-processing and actually some analytic on the spot? And obviously, hopefully that you realize that probably my interest is more on the lower one than in the upper one. Yeah, to make a priority, pervasive analytic, and hopefully, as I said, borrowing from the presentation this morning, come and develop some invisible analytics. So, I don't know how long do I have? 15 minutes, hopefully I'll finish. So some few real-time monitoring applications. You have here some few of the, actually all of these are works that I've carried. 2 or 3 of them are actually showing you exactly how this structural generative description is being applied and how the outcome. The other ones are just showing to you, because we're parts and parcel of the work that I was doing, the fact that actually I can implement real-time extraction of probability density functions of time series. Yeah, so there is a mix there, but if you want, we can go. We can go a little bit in depth if there is any doubts. So again, as I said, I'll take this document just to highlight here that in fact there was a group of experts there discussing it, and effectively I was doing something that may be related to that document. Again, it's not an exhaustive document in terms of the case study. It's an excellent document in terms of the suggestions as to how the government and the industry needs to collaborate, and education needs to collaborate. So I recommend reading it. It's quite interesting. So in terms of healthcare, what I have, if you want, the solution that I'm going to show you probably can be classified as prevention and early identification. So again, here you have the structure of that I've just mentioned to you. What you have here is an electrocardiogram. And for the ones of you who may have been involved in this, amazingly enough, I was not aware, our ECGs are unique. Yeah. So I can identify different persons by our ECGs. What is interesting, and actually that's implicit or is part of the Internet of Things, is that obviously we age, so our ECG also changes. So that's even more interesting, and that's actually a quite interesting feature that Internet of Things brings to us. Yeah, because series are not going to be stationary. Remember, the things that I'm analyzing, you name it, stock market, even the profiling of a person when he's a teenager, it will be different. When he have his family, it will be different when he ages. Yeah, so that person needs to identify as a unique person. So it's not that straightforward. Yeah, but just taking into account this. So what we did here, and this was just to prove, by the way, that our representation was robust. First of all, that time series is not stochastic. You can see that. Yeah, and ECG is not a stochastic series. Yeah, it has correlation. You see there. There are 3 different 4 or 5 phases. So we were able to make it quite well. It's quite robust. This has not been published because of other issues related with the subjects and the fact that we need to clear up this. With the institution and the place that we need to publish. But you can see here the different classes have been nicely identified. The idea here, first of all, was to identify different anomalies within your heartbeat, but also to be able to identify if you come on an emergency, you're coming to the hospital, I take you the ECG, you cannot talk, I will be able to go into the database and write, yeah, this person, we know him, yeah, this person is this or that, and he has this in the problem, he has been here in this hospital. Yeah? Or if it is a national database. So that was a little bit the idea behind that work. I mean, ultimately for us was the idea to prove that our representation actually can span amongst different different domains. In terms of buildings that we have also mentioned it quite some few occasions before. I want to show you some aspects of design, optimizing, and security and safety. And here again, the notion here, I will show you 2 different examples. The first one is what happens when things deteriorate. Yeah, what happened with vibration? So here you have an example of health conditioning, and you can see there that the red line here is actually showing you the characteristic of a motor as it ages. The interesting thing is actually that it's not static, first of all. You see, as it ages, it has different characteristics. There will be a point, obviously, in which you say, yeah, this is enough. Either I have to throw this motor away, or I have to replace it, or so on. But the point is, again, that I need to learn this. Yeah? If I want to make conditioning monitoring, I need to learn this. It may be that as you age, you need more often maintenance, and so on. So you can do that. And actually, that's published. That's the paper that we published together with other things. So this actually, we took this information from the Western Reserve University Bering Data Center, in which actually they have different types of sensor in different motors, and the motors that they were aging, yeah, you could actually sense them, and you can actually identify what sort of maintenance needed, and so on, if they needed it or they didn't. Together with this, another problem, which is a civil engineering problem. You have a long conduit, for example, carrying water underneath our streets, a long conduit carrying oil, some sort of liquid. Due to vibrations, for example, natural vibrations from the street, it may be a bridge too, yeah, vibrations on bridge. There may be an imminence that, for example, water pipe may break and eventually will flood that particular part of the town. So this was a small experiment, yeah, so it's not in real life. We didn't flood any street. But what we have is a long conduit. We have some sensors in it. You see here that there is some, you will see here that there is some correlation between them. And what we started to do is to make different sort of variations into the tube. And let me see if this works. So you have 6 sensors there. Actually, I didn't mention to it. Well, here they are the 6 sensors, but effectively, you see what you have here is actually different patterns in terms of the representation. Now, to be fair, the only thing that I show you there is the fact that I can obtain the PDF in real time. So I have not done the structural genetic decomposition, but remember the structural genetic decomposition is actually decompose first the signal and then get the PDF. In this case, I'm just getting the PDF of the signal. Yeah, but this is just an extra step. The only thing that I wanted to show in this particular slide is the fact that we have 6 sensors there. I'm not sure if that is normal or not, but what you have there, you see the 6 sensors with normal. There is some sort of correlation. They're relatively similar. Let me just move on this because I think this is about 20 minutes. Let me see if I get you some non. Yeah, so we have here, you see, you have here, what we did is to fan, a little fan attached or very close to the pipe. The pipe started to move, and you see immediately there that there is a different pattern in terms of the representation, yeah? So this will be an extreme case in which the representation only have one decomposition, yeah? In other words, we just filter the complete signal rather than to filter the signal into 3 or 4 components. But you see there immediately, you see that the sensors actually are showing different things, and they are correlated in a way. You see there that there are 3 and 3 correlations. And this continues. This is about 20 minutes. And here I just show, I'm not going to go into details, but obviously the study as to how many sensors I can lose before the information that I have has certain meaning. So again, that comes with the Internet of Things too. Yeah? I can deploy sensors. I can deploy actually quite a lot of sensors if they are cheap, and I can afford to lose them. Yeah? As opposed to deploying quite expensive sensor and not be able to lose them at all. Energy, this is another extreme. It's probably not entirely related to my representation, but it's actually extreme. And the extreme is in terms of, as a previous speaker mentioned, we have little data here that eventually may become big data. So, and the little data is all what we're extracting from these little sensors, either in the civil, either in towns, either from the set of motors. So one idea that I have had even previous to this is what can I do to actually keep the little data as little, or even smaller than little data. So this is an extreme, and this is what I'm trying to show you here is a problem of actually how to coordinate electrical vehicles in a grid. We're talking here about in London can be, in the future will be 1 million, I don't know, 500,000. They will be connected in a distribution line. Now the distribution line has a physical capacity. So when people come and say, look, these are just agents, we just need to coordinate agents. Well, now we're all realizing that that's not the case. It's not just about coordinating vehicles, because if you just coordinate it, that you don't realize that if you put 10 of those vehicles in one line, you will burn the cable, basically, yeah? So there needs to be some physical constraints related. Yeah? And so there needs to be a feedback between the grid and actually the place in which these vehicles are attached. So this is an extreme. An extreme here because what I wanted to do is a distributed algorithm that actually there is no communication, that everything can be solved on the site, totally independent. Yeah? I understand that there are some interesting patents, unfortunately already, in the US, very recent, which are claiming that they can measure locally exactly the same signal that I'm claiming here, that if you have that signal locally, you don't need any communication, which will be the ultimate Internet of Things solution without any data, without any big data, without any data that I need to process locally, centrally. So this is a problem. You have vehicles there, as I said. If you have vehicles and you charge all of them at the same time, one bit of the wire will actually blow up or will burn if you're not careful. So the problem was to do this was to be able to solve the level of the socket at the level in which the vehicle is connected, and to solve this very simple problem: do or can I charge? Or the only thing that I can do is discharge. In other words, because I'm an electrical vehicle, I can give also a little bit of my charging back to the, on one very simple signal, and the very simple signal is actually frequency deviation. For the ones of you in a little bit of power, you know that there is tiny frequency deviation. Actually, that is a signal that the network is either overloaded or underloaded. Yeah. Now the problem here, the technology problem was, can we have a device at the level of the socket which can actually tell me that? Yeah. If you don't have it, which is what we're assuming here in the paper, in this paper by default, you will need some sort of communication, but it's minimum. It's not a PDF. It's actually quite minimum. Yeah. It will be some signal, which is a central signal, but it can be broadcast like a heartbeat, saying the grid, I'm okay, you can charge, or I'm not okay. Yeah. And depending if you're okay or not okay, the socket will just solve a particular problem there at the level of the socket, and the cars will actually charge or discharge. Yeah, I'm almost there. This is just to show that even if the vehicles don't know, this is 1,000 vehicles, actually they will converge in less than a minute to the solution. Now, in terms of transport, which is the last issue that I want to mention, have been very interesting for quite some time. And this is with our colleagues here at NECTEC, on some sort of increase in safety. So here we have a classification, for example, of vehicles anomalies in terms of vehicular traffic, and some sort of spatial inference on traffic condition. Again, the fact that you may have many sensors along the way. What happens if one of those sensors breaks down? Can I live without that sensor until the sensor is repaired? So, oh, sorry. Not only we know that this is already happened, I mean, the vehicles now can have quite a lot of power. Actually, vehicles now can be clouds themselves, especially if they go into a parking place. You can have clouds of vehicles solving particular problems, but also they have the capability to talking to amongst themselves. And again, what we're trying to do here, this is even predecessed this, even though we knew that this was coming, is to try to actually be able to solve a distributed anomaly detection problem, which in the event, because I'm using sophisticated and online classification of actually certain relationship between vehicles across me, I personally will not be necessarily able to detect that something is going wrong. And obviously, this is not an incident. If it is an incident, it's like trivial. No, you don't need to do any signal processing to find that it's an incident. So the problem is road that probably all of you will know in a condition which is very low traffic, and the relationship between those vehicles, which we refer to as micro statistics. In other words, for example, is distance between vehicles, acceleration between them, and other micro statistics in terms of traffic, they will change. Yeah? And as I said, the vehicles, one particular vehicle will not realize that. But the fact that a group of vehicles is analyzing and they are able to collaborate, they will realize that something wrong is happening, even in very low conditions like this, because obviously that's the challenge of the fact that we want to detect an anomaly. Yeah? For any practical purpose, again, this may not affect anything apart from security, obviously, and the life of one person there. But that sort of problems are actually quite interesting. That can be automated. That will be effectively, this is a solution for a M2M solution within a set of vehicles, which can be automated. And the other one is as I said, what happens if I lose one sensor there, and what sort of analytics I need to play. The last one is, we have 2 minutes? 1 minute, sorry. So very short here. The last one is about the real-time construction on an environmental monitoring. This is, again, very short because I want to show you the last one. And I need to move this on. It's just to show you, this is a vehicle. This, by the way, if you don't know, this is Imperial College here. This is the college, and the vehicle just went around an area which is with quite a lot of traffic, and actually what you're seeing here is the real-time series, and this is the PDF. Yeah, so what we're extracting there, or what we're trying to show here, is that the PDF can actually be obtained in real time. What is important here, you see, is that this particular point here, we will not be representing that point in order to classify it by its time series up here, but by its PDF representation down here. And the last one, which actually is quite complex, even though it's a very interesting idea, but it's quite complex, is the fact that I would like, for example, this is again the college here, but I would like to have a system which, with the help of fixed sensors, which are red, these are bus stops, and the green sensors, which are either people that are moving, this is collaborated sensing, yeah? People that are moving, bicycles, motorbikes, you name it, people that is coming out of the tube station that is somewhere down here, they actually agree or not agree to collaborate. There are two extremes. One, which is called non-control, which means I don't ask anybody. If they move around the area, they will give me information. The other one is that I will be able to do some sort of agreement with a person that is coming from the tube station. Can you please go to that street and come back to it? But the key issue here is actually to detect in the minimum amount of time what is the incident of that, for example, pollution spillage, yeah? It can be anything in this case, it can be anything. And obviously there is an intelligent algorithm that is trying to give a target. This is the more sophisticated one. On the one extreme, it's trying to give a target on the mobile sensors, yeah, where to go, if they agree to do that, yeah? There is, I'm saying that this problem is quite rich in terms of research, because if you don't have any agreement with the person that is moving, not the fixed sensors are in the bus stops, but the people who want to collaborate, obviously you have all the areas of compressing sensing techniques in order to infer that area. On the other hand, if you have a partial control or intelligent routing, which is the blue, you have all other aspects that you would like to do, which is intelligent routing and so on. But it's very rich in terms of things that we can do, and all of them are based on real-time processing. And that's it, I think. Even though I wanted to show you something, a quick snapshot, as you saw there, or you may have not seen, but all of what is coming in, the Internet of Things, is not only bringing all these nice new things that we have to do, but obviously the traffic will also change. There will be profiles there that will be present that we will have to cope with. In agriculture, apart from putting the slide, I haven't done anything, so it's good, because we want to finish. So just in a snapshot, we, as I said, remember, the main idea of this talk is to try to do something on the velocity aspect of the Internet of Things, try to understand the pervasive and the invisible analytics, the trade-off between analyzing signals on the spot rather than on a central location, and to help to cope with big data problem by trying to keep as much data you could say that it's relevant data, but it's not irrelevant data because we have processed it, yeah, but try to classify the data that we want to actually retain or that we actually would like to process further, which will be the deep type of, deep analysis that was mentioned in the previous slide. I don't know, sorry about that, if I have 2 or 3 minutes for that. If not, we can